To start with string instruments, we kind of need to look at what standing waves are first. So, a standing wave is actually two or more waves that are constructively and destructively interfering with one another. And in the process of doing so, they create positions within the wave that are actually fixed and immobile, called nodes, and then other positions in the wave that have a dramatic amount of movement called antinodes. What we're looking at now is a half of a standing wave. Note that any point will either have a trough, like we see right now, or a crest, but we never have both. So this is half of a standing wave. Now, what I showed you here with the blue and the orange is actually the positions of the two different waves as they are overlapping. If you pay attention to the ends of this on the left and right side, you notice the blue and orange waves are always opposite of one another. But then in the middle, you'll notice that the blue and the orange waves are always directly on top of each other. What that results in is nodes at the end here and here, and an antinode in the middle. Now, if I want to look at one full standing wave, this is going to have three nodes for me, one on each end and one in the middle. As I increase, I get more nodes, more antinodes, and the process goes on and on and on. Now, our focus for today is on string instruments. So when we think about a string instrument, what we have to keep in mind is you have the string being pegged down on one end and then pegged down on the other end. So no matter what, you have to have two nodes on a string instrument. This is the least amount of a wave that could be shown on a string instrument, which is half of a wave. So if the string has a length L and we're looking at half of a wave, the wavelength would be 2L. The next possible wave I could do on the same string is a full wave. The reason is because I must end on a node, which means I have to end at an equilibrium position. So going from this first setup to the next setup, I have to add half of a wave, so plus half of a wave. My new wavelength is L. If I continue onwards with this process, I'm adding another half wave, and now I have 1.5 waves. Again, by adding half of a wave. We'll often call these loops, and you'll sometimes see this dotted version of the loop along with a solid line. The dotted line does not mean, so for example here, this does not mean it's a full wave. The dotted line is showing the other extreme position that the wave can take. Here we have a wavelength of 2/3 L. Now let's talk about the speed. The speed is fixed. The speed of a wave on a string actually depends on the string's mass density and the string's tension. Now, mass density is nothing more than how many grams per centimeter or kilograms per meter that the string material is made of. And then tension is how tight have I wound the string at the end here, creating tension within this. By going to half a wave, to 1 wave, to 1.5 waves, I don't change the speed. What I notice is my wavelength is decreasing. It started at 2L, then to L, then the 2/3 L, which means my frequency is going to be increasing. This first frequency is called the fundamental frequency. The fundamental frequency in the music world is also known as the first harmonic. The first harmonic occurs the first time you get resonance. Resonance, we talked about in the previous class. Think Tacoma Narrows Bridge, suspension bridge, child on a swing. Resonance, in terms of a sound perspective, right now you're not getting that much resonance from my voice. Consonants don't really make resonance. D, k, s, t. These consonant sounds, they don't create resonance, but vowel sounds do. You can hold a vowel sound like A, E, O. That's resonance. And that's exactly what we want to create on the string in order to create a nice even tone playing the instrument. The first time we do it, we call it the first harmonic. Now, what will happen as we add more waves, the frequency just goes up 1, 2, 3. First harmonic, second harmonic, third harmonic. So let's say, for example, I want to know what is the frequency of the seventh harmonic. Given this string has a length of 50 centimeters, determine the frequency of the seventh harmonic. Speed on the string is 450 meters per second. So I would be saying, all right, looking at the very first scenario, I see that my first wave, which is a half, is 50 centimeters. Therefore, the full wavelength would be 1 meter. So at a wavelength, 1 meter, a velocity 450 meters per second, V is lambda F, 450 equals 1 F. F is 450 hertz. Now that's the fundamental frequency. So at the seventh harmonic, 7 times 450 is going to yield 3150 hertz.